How does the sun shine? Often, when something glows, the light comes from a chemical or electrical process. But the sun, like all other stars, gets its light from nuclear fusion, primarily through a path called the proton-proton chain. So how does this work? Matter here on Earth is made up of atoms, which have one or more electrons bound to a nucleus. A nucleus is in turn made up of protons and neutrons. The sun is mostly plasma, which means the electrons are separated from the nuclei. These nuclei are primarily either single protons or helium nuclei. The sun's light energy comes mainly from the proton-proton chain, which begins with the fusion of those protons in its core. When two protons collide, they usually just bounce off of each other. This is because they're both positively charged, so they repel like the north poles of two magnets. But every once in a while, a collision causes one of the protons to release its positive charge and become a neutron, and the particles stick together to form deuterium. Once this happens, a little energy is released. This is step 1. In step 2, another proton collides with deuterium, creating helium-3 and releasing more energy. When a proton converts to a neutron in step 1, it releases two particles, one called a positron and the other an electron neutrino. The neutrino is its own story, which we'll come back to shortly. So far, we have helium-3, but one of the most stable nuclei is helium-4, with two protons and neutrons each. Occasionally, two helium-3 nuclei will collide and form helium-4 and two extra protons. This is the last step of the chain, and it releases the most energy of all. The energy released by the proton-proton chain doesn't come in the form of light we can see. Instead, it takes a long trip through the layers of the sun, getting absorbed and transmitted through its plasma over thousands of years. Eventually, the energy reaches the sun's outer layers, leaving the sun in the form of the light we see. The total energy output of the sun's fusion is immense. In a single second, it's a bit less than 400 trillion joules. That's enough to power the world for over 4 million years. We now have an idea of how the sun shines. But how do we know this theory is correct? We can't send a probe inside the sun's core to check because the immense heat would melt it long before it got there. However, earlier we mentioned that the sun makes particles called electron neutrinos through fusion. If we can find the right number of electron neutrinos coming from the sun, then that's one thing that supports our theory. There are 3 types of neutrino: electron, muon, and tau. Though we saw that the sun only makes electron neutrinos through fusion. Neutrinos are an unusual kind of particle. These ghost particles are very light, so they move very fast. They rarely collide with other particles, so they can pass through solid objects without being stopped. Most of the electron neutrinos from fusion escape the sun completely, and some of them reach the Earth. But it's very hard to find them. It took special equipment and a lot of time, but the Homestake and Kamiokande 2 experiments detected these solar neutrinos. Even then, however, these experiments saw only 1/3 of the anticipated number. Why is this? It turns out that one type of neutrino can change into another over time. This is called neutrino oscillation. As electron neutrinos travel away from the sun, they change to muon or tau neutrinos, which can change back and forth and so on. By the time they reached the Earth, 2/3 of the neutrinos were the muon or tau kind, which older detectors couldn't see. Newer experiments like SNO and Super K were built that could see all 3 types of neutrino, and they confirmed both the fusion theory and the neutrino oscillation theory. They've also given us some information on neutrino properties, like how heavy they are. There's still a lot we don't know about neutrinos, but their oscillations can give us some insight.